Hi folks, welcome to our last video for our 12.7 lecture series. And in this video, we're going to take a look at identifying shapes from a rectangular equation, but then taking those rectangular equations and converting them to their spherical form. So let's get started with part A. All right, so I've got z equals the square root of 25 minus x squared minus y squared. And I know that if I'm trying to match things to the graphic organizer on quadratic surfaces, there weren't really a lot of square roots. So if one whole side is square rooted, it might actually be beneficial to just go ahead and square both sides. So we can kind of start to see what shape we're looking at, okay? And I do notice that all three of these have a power of 2. And so that might be a good clue that we're not looking at the elliptic paraboloid, but rather something that has all three components are squared, okay? So I'm going to do one more thing. I'm going to take my x squared and y squared, and I'm going to add them to the same side as the z squared. So I get x squared plus y squared plus z squared equals 25. And so with a little bit of algebraic manipulation, we see that the equation we had originally was actually a sphere, okay? So it's a couple things. It is the top half of a sphere, right? And in particular, it's not also the bottom half of the sphere because there's no negative in front of the square root. So the positive square root, that gets us the cap of the sphere, and then the negative square root would give us the bottom of the sphere, okay? So it is the top half of a sphere with the center at the origin, okay? And another good feature to talk about when we're talking about a sphere, what is the radius? And that radius would be 5, okay? So we've got top half of a sphere, center at the origin, and the radius at 5. Now, let's talk about how we can convert this to its spherical form. All right, so I'm going to take this equation, the one where we had sort of manipulated things, and if I look at my graphic organizer, x squared plus y squared plus z squared is the same as rho squared. So I can replace this whole thing, this whole left-hand side with rho squared, and I still have equals 25 on the right-hand side. We're going to go ahead and take a square root. We technically have two solutions, but we don't really define that the distance as a negative value. So really it's rho equals 5. And this is the equation of a sphere in in spherical coordinates. So think about the name, right? A sphere is actually a much more simple equation in spherical coordinates than it is in rectangular coordinates. Okay? All right, let's take a look at one last one. I think this one will require a little bit more algebra up front, but let's kind of see what happens, okay? So if I go ahead and do the same idea, maybe I can square both sides, right? So I'm gonna square both sides and I'm gonna end up with z squared equals 3x squared plus 3y squared, right? Now, I notice again that all the powers are squares, so I'm not thinking that this is an elliptic paraboloid, okay? Instead, let's kind of go back to what we had earlier. It's also not like x squared plus y squared plus z squared, like they're on different sides and we're not adding or subtracting all of them. But where did we see something similar? Over here. Okay, so it turns out in this case, we're going to have a cone because it's of this form z squared equals x squared plus y squared. Okay, so this is going to be a cone. It's going to be opening upward, but our x and y's are going to be just like a little bit wider than they were in part B from example number 4. Okay. Now, how do we convert this into our spherical form? We got to get rid of our X and our Y and our Z. And instead, we want to have like rho and theta and phi. Okay. Sometimes I find it helpful to make a little layover in cylindrical land. And then once I've gotten into cylindrical land, then I can go from there into my spherical land. And here's what I mean by that. So I've got Z squared equals, I'm going to factor out a 3. And when I factor out a 3, I'm left with x squared plus y squared, which I can replace with r squared. And then from there, I can go ahead and take the square root of both sides. Z equals r times root 3. And we'll take just the positive one here because we're looking at whether we have uh, like if we're defining r to be positive or negative. Okay, so we'll consider it to be positive. But what I find really helpful here is I can go now convert from cylindrical to spherical. Okay, so this is sort of our cylindrical one. And from here, let's continue on, make some substitutions and get into spherical land. So I know that Z is the same as rho cosine phi. And I know that R is the same as rho sine phi. And I have this root 3 hanging out on the back. Okay. So this Z is the rho cosine and the R is the rho sine. And then that root 3 is just the root 3. And kind of like we've seen a lot of uses of the zero product property, I'm going to go ahead and move this term to the left-hand side, set it equal to 0, and factor out a rho. Okay, so I'll get rho of cosine phi minus root 3 sine phi is going to equal 0. And this zero product property, because like if we had divided away the rho, we might have lost a solution. We don't really know. But in this case, we get rho equals 0. That's just a dot like at the origin. So this one actually doesn't give us any solutions at all. This is what we call an extraneous solution because it's just a point at the center, and that's not what this whole shape looks like. Okay. But we do have this other part to consider. We've got cosine phi minus root 3 sine phi equals 0. I'm going to go ahead and add that root 3 sine theta to the other side. And then we've got cosine theta phi equals root 3 sine phi. I'm going to divide the cosine to the left, and I'm going to divide the root 3 to the right. And I'm going to get 1 over root 3 is sine phi over cosine phi, which is tangent phi. Okay. Now this is a very nice trig unit circle value here. Where does the opposite over the adjacent equal 1 over root 3? We do a little bit of work, and that should be pi over 6. Or we could envision it as 30 degrees because those two are equivalent, right? So depending on how much we want to be able to visualize this. And so if we look at what we have here, okay, this equation, again, totally fine and rectangular. Look at all this work we had to get to the spherical form, but one of these seems like it's going to be a lot easier to integrate or differentiate than the other. And I hope we can agree that like phi equals pi over 6 is just going to be easier to work with, okay? Now, let's remember what phi is before we leave this video. So we've got our x, y, z coordinate, right? We've got our x, our y, our z. And so when we say phi equals pi over 6, we're saying from the positive x-axis, we're dropping down an angle of pi over 6, and we're doing that all the way around. And so that's where we can start to see that we're getting a cone, okay? All right, so let me get this all on one page for you. But I think some good practice in terms of converting and maybe setting forward this idea that just some coordinate systems are going to be easier to do the calculus with, which is why it's important for us to go ahead and be able to convert between the two. Okay? All right, let me know if you have any questions.